Good morning. My name is Recep Avcı. I'm a physicist and director of Imaging and Chemical Analysis Laboratory. Today I will talk about 4.6 billion years of Earth's history. And good morning to you again. If you take a look at sky on a dark night, you see billions of stars. You can see a lot of stars here. You see my pointer, good. And then not so much here. It is because you are looking at the Milky Way. Milky Way is a huge collection of stars. There is 250 billion of them. And the distance from one end, that's a disc-shaped spiral galaxy. It takes 100,000 years at the speed of light to cross the Milky Way. We are located right here. It's about 35,000 light years from the center. Center of this collection of stars is very violent. If you were to live very near it, life as we know would not have happened because there's a black hole here. Stars kind of disappear into it, and there are lots of gamma rays, energetic particles. It would have killed everything if we were very close. So we are not in a danger, and then our sun revolves around the center here. It takes about 230 million years to complete a revolution. So if you look at through a pinhole into a dark corner of sky, this is what the Hubble telescope shows. You see all of these white spots. Each one of them is a galaxy. And in this field of view, this is 30 millionth of a whole sky. There were 5,500 galaxies they count. Do you hear me okay through this mask, or since you are far away, I may maybe take it? Okay, thank you. But if you count whole galaxies in our universe, there is no less than, this is the visible ones, the ones that we see. There are ones that we don't see. There will be 150 to 200 billions of them. Well, each galaxy is something like that. And each galaxy you have hundreds of billions of stars, and you have hundreds of billions of galaxies. So we're talking about billions times billions of stars in the universe. It's a fair question to ask whether there's life in one of these around, there's some, each star has planets just like Earth. The nature of how these planets form guarantees there will be planets around each star. So is there life out there? The answer so far is not, but there's a huge activity to make sure that we can actually look everywhere. So let's focus on our Earth because this is the topic. So this is the picture of Earth looking from the moon. And you can see it's the heaven in the universe. That's the best description of it. I want you to pay attention to this very hazy atmosphere around it. We live in that. It's about 10 kilometers from the surface. We come to classes, we go picnicking, take our dogs to walk, and we go movies. We live in this little bubble here, which we call atmosphere. Earth, you will see through my lecture, went through 5 very serious extinctions. And our neighbor, Venus, it's the hell in our planet system here because it went through an extinction about 700 million years ago. It happened to be a runaway greenhouse effect. And right now, we cannot, when you look at a picture of it from Earth, you don't see it like that. You see just a ball. A thick atmosphere about 50 miles across. Carbon dioxide and the loss of acid is a poisonous environment. The surface of Venus is about 400 to 500 degrees centigrade. It'll fry you. And the pressure on the surface is like you're living 1,000 meters underneath the sea. It'll crush you. So we want to make sure that we don't contaminate this very narrow layer of air that we live in. It is absolutely necessary. And you will see if we lose control of this, it takes millions of years to recover from it. So what do we have in our solar system? We have obviously planets. There are 4 rocky ones and 4 gaseous ones. But there are also all kinds of rocks. They are from nanosize. They vary from nanosize to thousands of kilometers across, huge boulders of rocks. It's called the asteroid belt. It's located somewhere here, and there's another one out here. There's another one down here. The comets come from this Oort clouds. They are mud and ice. They go through an elliptical orbit once in 100 whatever years. But most of the stuff rotates around nearly circular orbit, and there is a lot of these particles. Sometimes they fall on Earth. In fact, there's every day some meteorite fall on Earth from that. Here is the one that we analyzed. This came us from University of Washington in Seattle. That's a nanoparticle. This particle was around before the solar system was formed. 4.7, 4.8 billion years ago. Solar system was formed 4.6 billion years ago. And you can see it's sub-micron or nano-sized particles huddled together. They are not smashed into each other. They are just basically touching each other. We analyze the content of this. There are magnesium, aluminum, maybe some silica there. This was there before Earth was there. It's here really. The sun, this is where our energy comes from. So the center is very hot, about 15 million Kelvin. By the way, let us get used to this Kelvin unit of temperature. Right now, room temperature is about 300 Kelvin. So when I say Kelvin, we start from 300, and then you go down. Minus 273, zero corresponds to minus 273 centigrade. So that's the unit. I'll refer to it as Kelvin. So center is very hot. Surface is about 6,000 degree Kelvin. And the density of this is mostly made out of hydrogen and helium. Sun uses thermonuclear reactions to generate energy. It converts the hydrogen to helium. Helium to essentially collects the protons and neutrons from the hydrogen and helium, makes other atoms in our periodic table. All of our elements was produced at the center of the sun, and while they are dying. So all the elements in the periodic table are made here. When the universe was created 13.6 billion years ago, there was only hydrogen and helium after about 400,000 years of its creation. Everything is made in the centers of stars. So we are made in star. And there is solar radiation. This corona ejections, sunspot activities, they are very dangerous. They are very energetic particles coming to us from the sun. But thanks God, we have a magnetic field. They don't reach us. If they did, life would not have happened. For example, Mars does not have a magnetic field. These particles strip off its air, whatever, in the atmosphere. So it's very important that life depends on this protection. So if you look out into sky, about maybe 1,300 light years away, if you have the right camera and right sensors like infrared, you can see these kind of clouds. These are called the nebula. These are a collection of diffuse gas and dust particles, nanoparticles, and they are mostly hydrogen and helium again. But it's spread over hundreds of light years across. And it's like vacuum there. It may look like it's very dense, but it's not. It's like right now here we have in 1 cubic centimeter 10 to the 19 atoms, air, nitrogen, whatever. Right there, there are hundreds to maybe a couple thousand. So it's vacuum, but from here it looks dense. So this is all the material that's needed to make a solar system, to make planets and living things like us. So this is the beginning to establish a star and then planets around it. Let's take a look at one of these nanoparticles in those clouds, dust particles. Here is one. This is about the same size that I was showing you earlier that we analyzed in our laboratory. For example, typical, besides, as I said, there's mostly hydrogen and helium there, but there are these materials. They were essentially spread into space when the sun and all the planets around it died. So at the core of this is very cold there. Space is very cold. An empty part of it with no gas particles is about minus 270 degrees centigrade or 2.7 Kelvin. But these particles are a bit hotter. They are about 15 Kelvin or minus 260 degrees. So there is a frozen water, hydrogen, the carbon dioxide, monoxide, all these hydrocarbons, amino acids stored on the surface of these nanoparticles. At the center, you may have silica or iron, all as metallic or other minerals. On the very outer crust, you may have polyaromatic hydrocarbons and etc. So everything, when our solar system was formed, these things were already there. So how does the solar system form? This is what happens. You have this solar nebula. It's a collection of dust, and as I said, I show what is in there. But it's spread over a couple light years across. And at certain temperature and pressure, their common gravitational forces pull this one toward the center. And these nebulae are dynamic. They rotate a little bit, but as you can see that if things get smaller, angular momentum is preserved, things start spinning faster. So essentially, all the material here condenses at the center, so much so that nuclear reactions start, a proto-sun is born. All the material that's around it forms in a disk, and they are revolving. They are the nanoparticles. They start coalescing together because they rub against each other, they are charged, and they start getting together. But when they grow, their gravitational forces essentially make the planetesimals, these rocks collections, they are spinning, and essentially the planets are formed from this interaction of these particles. So a proto-sun is formed, the protoplanets are formed. Give them time, you will have our solar system. This is what happened. This is very important, and a typical life cycle of a star, this is what will happen to our sun as well. There is this nebula, a collection of dust and particles and things like that. They essentially, it depends on the size, you can have a huge, massive star, like this one here. Our universe has all kinds of stars, very small ones, and their surface temperature depends on how big they are, and very large ones. But most of the stars are small ones, smaller than even our sun. There are giant ones. So let's look at these giant stars. They don't live too much. They are very inefficient. They spend their fuel, which is hydrogen, and they essentially first expand and then explode. These are big stars, and they only live millions of years. And you don't want to be around one of these things. And then the core of the star condenses to what we call neutron stars. The size of this town, But the density, if you take 1 cubic centimeter of this neutron star or black holes, it'll weigh 1 cubic centimeter will weigh about 10 to the 11 kilograms. Unbelievable. Or a small star, depends on the size. So like sun, they live billions of years. Our sun has another 5 billion years. So they essentially run out of fuel. They get hotter as they go, and they explode, and they turn into a white dwarf, size of Earth. So sun, most of the material at the center becomes white dwarf. It's a very hot ball, essentially floating in space, but size is size of Earth, sun to Earth type of condensation. Other materials become another source for a new star. Every year in our galaxy, 1 to 10 new stars are born. You can actually observe them. And the density of this white dwarf will be like 10 to the, if you take 1 cubic centimeter of this, it'll weigh 1 ton. And material here probably made out of carbon or silicon, whatever the last material that was taking place at the center of this sun. So let's come back to Earth. So after the planets formed, our Earth was a molten hot ball. So what happened here, it differentiated. Essentially, it's also spinning, and heavy atoms went to the center, all the nuclear radioactive elements that contributes to the heating of our Earth, and mostly iron. And so you have a very hot core, about 7,000 Kelvin. This is hotter than the surface of the sun. In fact, if we were able to travel to the center of Earth, you will see a bright sun type of brightness. And it's solid because pressure is so high that it cannot stay in a liquid. But there's an outer core, which is, again, the same material, less pressure, is liquid. Because of the liquid there, that's what causes formation of magnetic fields. Weak, but thanks God it's there because we are here because of it. But what happened 50 million years after it? This was 4.6 billion years ago. So what happened? There was another planet size of Mars collided. Imagine the situation. Mars is colliding with Earth. That particular planet was called Theia. And you can imagine the situation here. And some of the material just, essentially is scattered in space, formed a collection of particles around our Earth. Some stay on Earth. Essentially, those material, they were floating around our Earth, become moon. So moon, turned out to be came to our life in a very early existence of our Earth. So let's look at what is the cross-section of our Earth looks like. It's very hot at the center. It's solid. It's about 6,000 kilometers from the surface. And there is this outer core, liquid, and there's this mantle. It's not liquid, but it's not exactly very solid. It's a pliable material. The crust, all the sea and the land is where we live. This kind of can slide over it. And hence, there are plates, and they move relative to each other. I'll talk to about, and that's very hot. It gets very hot as a function of temperature, distance. So we have this magnetic field protecting us against these energetic particles that's coming from sun. And that's down. If you go up, that's what I'm saying. We have this very narrow layer of air. Better keep it clean, otherwise we are doomed. And surface, and if you go 10 kilometers, temperatures get very cold. That's what the temperatures sometimes are given on the plane. And then there is ozone layer. Thanks God we are protected from UV lights. And then it gets warm again, gets cold again, warm again. Don't worry about why it has like that, but this is the upper atmosphere. So let's look at a little bit about the dynamics of this mantle It's not static. The material from here can be transferred up to the surface. You get magmas of volcanoes and things like that. And there are these plates. These are Earth essentially moving. One plate moves against the other one. And that essentially, in the history of our Earth, these plates are not where they are right now. So they move against each other. This causes earthquakes, or away from each other, or towards each other. When they move towards each other, there are this subduction, like in the Washington area. One land goes in under the other one. But what happens that this material from the crust mixes into the mantle, and so there's always a mixture of material from the surface of the Earth into the mantle, and they come back through these volcanoes. And mostly when they erupt, you have a loss of carbon dioxide. That causes greenhouse effect. That's what happened in Venus. That's how we lost Venus. This also happened on Earth, but we survived it. I'll talk a little bit about it. Here is the evidence of it. Over the history of 4.6 billion years of history of Earth, like 300 million years ago, this is how the land looked like. This is Africa, this is South America. They were all joined together. This is what will happen 250 million years from now on. They will all come back together in a different part of our Earth. So these lands moving around through these movements, and there are supercontinents in the history of our Earth. They form in different geometries. That's why sometimes you go to the Bridger Mountains, you see shells and things like that. Or you even go to the South Pole, you can see marine organisms on top of the mountain. So it's a dynamic process. I just like you to know when you sometime hike and you see a shell on top of the mountain and say, hey, how did it come here? We were sometime at the equator, sometime in the poles. This is what happens when you have these movements of tectonic movements of land pieces. So let's look at the history of our Earth, because we are interested in the living things. When did the life started? So 4.6 billion years ago we are formed, and Moon was formed, and the fossil, actually rock. People collect these old rocks, and they find these zircons. They are like micron-sized particles of zirconium silicon oxide. They are very tough. They are very tough not to crack, but there are some radioactive materials that essentially trapped in there. They can measure very accurately when this particular mineral was formed. They found these zircons about 4.4 billion, a couple hundred million years after the formation. Where there's a zircon, you can also look at the oxygen there. They also guarantee that there was water on the surface of Earth. So there was some water, maybe not a lot, not a lot of oxygen, oceans like we have, but there was water. If there's water and temperatures was pretty good, there's probably life. So hypothesis is that first life may have been created. How it was created is another story. We're not going to talk about it, but I'll talk a little bit about it, but not much. About 4.3, 4.4 billion years ago. That was all anaerobic. There was no oxygen. But what happens 2 or 3 million years after this formation, there was this heavy bombardment of our planet. It took 300 million years for it to cease and to stop. It essentially destroyed all the evidence of life that may have been at this time. This is called a late heavy bombardment. But the hypothesis is that life may have started here. Evidence of life, as fossil records suggest, after this bombardment. So why there was this bombardment? Because in Jupiter, there are huge gaseous planets, and Neptune, they were kind of in dispute they want to occupy, I mean, like everybody else, there were border fights. Their gravitational force, until they stabilize, was such that they will hurl these rocks from these Kuiper belt and asteroid belt onto anywhere towards sun, away from sun. Essentially, it took like 300 years for this to stop, and all the evidence prior to 3.5 billion years destroyed. And during this process, the water, carbonaceous Candoroid had been thrown at Earth. Water accumulated, oceans are formed during that time. Remember, all these dust particles, they have water in it, but you have to kind of release it. So that's where the oceans are formed. So let's get back to our life. Life started from one single cell organism anaerobically. Hypothesis is that there was these hot chimneys, at the bottoms of the oceans in a marine environment. Somehow, first cell started. They call it LUCA, last universal common ancestor. From there, everything else, as we know, on our Earth evolved. Bacteria, these are prokaryotic, and archaea, these are single-cell organisms. Difference between them is their cell wall. And then all the eukaryote, all the multicellular organisms formed here. But there is one common ancestor each one of us relate to. So for life to evolve, so it evolved and this happened. But for it to evolve, surface of the Earth, this is where physics come in, has to be at a stable temperature. You have to have liquid water. You shouldn't freeze it or you shouldn't evaporate it. There are two important, it also goes to the greenhouse phenomena. I don't want you to know the details, but I want you to know this. Any object that's hot, that radiates light, this is sun, it radiates at 6,000 degrees Kelvin. And so this is the maximum radiation comes in the visible, and the evolution essentially made us sensitive to that. But there's different wavelengths from UV to infrared, it's radiated. That's where Earth gets its energy, and plants and all the photosynthesis is there. It heats Earth. Earth gets room temperature, 300 degrees Kelvin. It also radiates. That's how Earth cools. If you have in the atmosphere things that Earth radiates, but if you absorb this radiation, Earth cannot cool. So that's the source of greenhouse effects. So it radiates into space, and then an equilibrium temperature is preserved. There are natural phenomena that maintains this temperature in the air throughout the billions of years of history. This is the most important one of them. So unfortunately, plate tectonics and all these volcanoes and whatever earthquakes are necessary evil for life to exist on Earth. So when volcano erupts, CO2 comes out, and then it kind of warms. This is a greenhouse gas, warms the atmosphere because earlier periods, sun was not as bright as now. Sun gets brighter and brighter. In fact, that's what will kill the life on Earth eventually. And then rain comes down, washes the CO2. It becomes acidic, goes into the ocean, goes into the sediments, and essentially goes back to the magma, and metamorphism process produce CO2, and then this cycle maintains. So when there's a CO2 in the early days, it warms the Earth. When it rains and you remove CO2, it cools. This cycle maintains the temperature, and this is what kept us essentially evolution to continue. So fate of Earth essentially will be determined because of this process. So we still have 1 billion years. Don't worry about, we are here for a while. But Earth still has about 4 billion years of life, but only up to 1 billion years from now on, it will become very difficult to live on Earth. And what happens, the sun will get a bit hotter. It will evaporate the oceans and water. It will become a thick greenhouse, and Earth cannot cool itself through radiation. And you will have these temperatures going up to 450. You cannot go and walk on this environment. Human beings still might be here, but they have to use their technology to cool themselves. So we still have a stable environment for another billion years. That's so this is the kicker. Great oxidation of our Earth. So everything was anaerobic. There was no oxygen in early period of Earth's history. But about 2.5 billion years ago, it suddenly, not very suddenly, it took them a couple of millions of years to, some of the bacteria, they were anaerobic, learn how to use, this is incredible. I mean, if anything that will raise your hair, it should be this. The bacteria that was anaerobic, they were in undersea, learn how to use sun as their source of energy. They learn how to use photosynthesis. That means they use this, sky was full of CO2. They took CO2, produced oxygen. And in the evenings, they take oxygen, produce CO2, but net effect, there was extra oxygen molecule each one of these cycles. So cyanobacteria took over the world, everywhere. It poisoned everything in their way, in the coastal regions of our oceans. It took over our world. They were the smartest. This algae, and particularly cyanobacteria, essentially start evolving very fast. So initially, oxygen was consumed by dissolved ions in the sea, like iron, and there are evidence of it. These are cyanobacteria, fossils of cyanobacteria, biominerals, dating back to 3.4 billion years ago. These are called the stromatolites in Western Australia. This is the evidence of banded iron formations. So initially, oxygen was consumed by this iron in the oceans, and they essentially settled down and they formed these rock formations. So they can easily date these things. They can tell when this was happened. So, and then there's no longer oxygen can be consumed in water. They start coming into air, in atmosphere. Suddenly we have now oxygen, and everything start using in their metabolic cycle oxygen. And it's very fast. You can create a large number of ATPs per oxygen cycle. Same thing with photosynthesis. So nature changed 2.5 billion years ago. So let's look at what happened. Right here, 2.5 billion years ago, oxygen, the Earth was oxygenated water and this atmosphere. But there is another 2 billion years it took for life to evolve. Initially, everything was single cell, and they start becoming unicellular. And there was no animals, as we know, apart till 500 million years from before. Everything evolved in marine environments. And life started showing its face from 500 million years from before. And so I will just talk a little bit about it, and then we will, stop this conversation. So about 500 million years ago, spread of algae and mollusks, and then fish and plants, then vertebrates, spiders. As time kind of comes closer to our period, animals are evolving. And then Carboniferous period. This is very important. This was like 350 to 300 million years ago. This is all the coal happened during this period, 60 million period. There was this tropical environment. You have swamps and marshes and all these kind of things. Trees are dying, but they are very huge, hundreds of meters trees. They fall down, but there was no organisms evolved to degrade them. So they went down under, they went underwater, high pressure temperatures make coal. Every coal in different parts. At that time, obviously, Earth lands were not like that. So you can, anywhere you see coal, it was created in these marshlands about in this 60 million years ago. But the petroleum is different. Those are the marine environments. They are settlements in the marine environment. But the coal is dating back to this time. So anyway, so large marine predators up here. and spread of large lizards and dinosaurs. So let's look at some of them. I'm going to talk about the five very major extinction events. So as a function of diversity of the organism that's starting about 500 million years ago to our time, diversity is increasing because of evolution. But every time when this yellow triangle took place, there was an extinction. This is a very important graph. It may not look much, but it tells you something. So anytime the diversity, when that happens, many animals or plants die, and then recover, and die, recover. This is a big one. There was so much volcanoes in the Siberian part of our world that it essentially killed a huge number of species, but they recover. The point, and this is where the dinosaur died. That's about 65 billion years ago. There was a meteorite fell in the Mexican Gulf, but that triggered a bunch of other earthquakes on the other side, and essentially global warming. It killed all the dinosaurs. It's a kind of blessing in disguise. If dinosaurs didn't die, we would not have evolved. So you can look at it both ways. Sorry they died. Maybe not so sorry we are here. Survival of the fittest. And but I want you to take a lesson from it. Every time an extinction takes place, like it is taking right now, let me go back to that. It takes millions of years to recover from it. Population of Earth is increasing. We are using cars and all this kind of fossil products. We are really contaminating Earth. Take this, don't make a political thing out of it. Listen to the scientists. We are not too far from point of no recovery. If we lose this battle against the global warming, we are doomed. We will not recover from it like another 10 years or 20. It will take thousands of years. Your kids, kids, everybody will suffer from it. So take it seriously. So let me give you some examples of extinction. I'm almost done here. So this was like not too many years ago, 100 years ago. This is called the wild pigeon, or the passenger pigeon. This continent had billions of these birds, but they were tasty, I suppose. People hunted them ruthlessly, and they have a good record of it. Last bird was shot in 1899. Last pigeon, wild pigeon, died in Cincinnati Zoo at 1 p.m. on September 1, 1914. There is none of this bird. We are ruthless animals ourselves. We really don't. I mean, why the hell leave a couple for the next generation? But there's not a bird like it's a beautiful bird. These, they were 10,000 or 12,000, 13,000 years ago during Ice Age. This is woolly mammoth, giant sloth, and the saber-toothed cat. They're always roaming in these lands, 10,000, 12,000, 14,000. Changing the climate and excessive hunting by smart ones like us, essentially, they are also extinct now. And these are, dinosaurs. We know what happened to them. These are the other animals. They existed. So 99% of all species, they live on Earth, extinct. In spite of that, we still have lots of. And these are other species. This is Permian period. This is 252 million years ago. This huge earthquake, the volcanoes that killed everything. And the marine, species, all of them are part of petroleum that we are using. And the plants in the earlier days, Earth was just a rock, and then it's colonized by the plants. And question we ask, are there places like that? So golden age of astronomy is coming. There are these telescopes orbiting. Until like April 2, 2020, there were like 4,000, more than 4,000 of exoplanets, possible life on outside planets have been discovered. It's being continuously monitored, and there's no sign of life there so far, but we are looking. This is a big one. Next year, they will launch this James Webb. They've been working on it for 30, 40 years now. And this is a big one. This is the biggest telescope that will be up in the orbit, about 6 meters. Right now, we have this Hubble. We have these beautiful pictures. They are about 2.4 meters. There's another one. It's like the size of Hubble. It'll be going all around and very rapidly, essentially looking, see if there's anything danger, like, for example, a meteorite coming to Earth, or interesting parts of the universe. They are equipped with next generation detector. These are Earth-based telescopes. They are huge. This is 40-meter European telescope in the mountains of Chile. This is in Hawaii. And so golden age is yet to come. Just enjoy the next 10, 15 years with that. Now, this radio telescope, this is the big one, 500 meters. They are listening to the universe in a signal that somebody might have been sending to us. With that, I would like to thank you. And if you have any questions, which I hope and I really wish you have, I am here for you. Thank you for your time. Come on, guys. Yes, please, go ahead. Sorry.
Wait up.
Hello, hello. All right, cool. Let's see. My first question would be, where did all the matter come from?
Can you repeat the question, please?
Where did all of the mass come from? Like all the electrons and so on?
Oh, okay. Very good question. So I have to talk to you a little bit about Big Bang. Everything came, so nothing is newly created. When the universe was created 13.6 billion years ago, all the electrons, protons, light, anything you can discover in these hadron colliders in Switzerland, anything on this planet came created at that time. So now, like the gold, titanium, or carbon, silicon, whatever, initially it was all protons and neutrons, essentially hydrogen and helium. But then at the centers of the sun, there's a large number of stars, it gets very hot. So fusion reactions, so protons or neutrons are available for you. They are fused together, make other elements in our periodic table. I will be teaching astrobiology class next week. I taught it last time. There are details that are here, how it's happened, but all the mass, everything you see here on Earth,
Okay.
it's created then.
Another question.
A bit of a follow-up. How did it all get there? I guess.
Oh, ultimate question. Excellent question. So how did it get there? Allow me a couple of minutes to set up the background. So right here you see nothing, is that right? But there's about 10 to the 19 air particles in there per cubic centimeter. Let's clean it. Let's take a big pump it. Let's go to the far reaches of the universe. There is no air there, nothing. What you say nothing is everything. All the things, there's so much material in vacuum, what we call vacuum, but they are matter and antimatter that annihilate each other, so there's zero energy. But if you so it's a quantum mechanical phenomenon. During that very brief periods, this matter and antimatter, it's not static, it's dynamic, they fluctuate. These fluctuations cause, it just went haywire for a second, and then they separated from each other. This separation created everything in our universe to make our universe. In fact, there is more materials than what you see when you look at the star. There's this called dark matter. It doesn't interact with you, except it's probably we have dark matter here. It is there, it has gravitational force. So it's only 5% of the total matter, the star. There are other matters that we don't see. They are topics of. You're asking very difficult question. Even the current best scientists try to answer that. But we know we are an accident. Essentially, these fluctuations in vacuum separated suddenly and the universe was created. Everything was in that little zero size volume.
So what are you doing in your lab?
I'm a material scientist. I analyze materials. I analyze your materials. Dave has these fascinating diatoms that they look like in other universe by themselves. We help, I mean, I do research, my own research. I do corrosion, and I try to understand degradation of materials. But we do material science. We have electron microscopes. We have spectrometers. We have atomic force microscopes. I really, it's a 339 Barnard Hall next to the Center for Biofilm Engineering. Stop by there. Come on and see what we do. We will show you.
Okay, where is your lab if they're going to come visit, and how do they
Anytime.
arrange
Look,
a visit?
So here's the thing. You go there, say, I want to see what you do here. If they don't show it to me, come to me, I'll scold them. They will show it. I tell people, we love to show our facilities, even some examples, when you come in. So this is not only a research center, it's also educational place. So we love to tell you what we do. This is our mission. It's our educational mission. Come and see.
So
Any other question?
Why are you interested in biotechnology?
Well, believe me, I even published in neutrinos and things like that, some of these quantum mechanical things. But I realized that really biology is the most mysterious thing. I mean, we still do not know how the life started. To me, it's a hair-raising phenomenon. It's that simple. It is just, I mean, look, I'm talking to you. Well, show me any place in the universe that people talk to each other like that. We are enjoying, we know our existence. We are aware of our being. So to me, this is the biggest mystery. I want to understand that. So I'm not exactly a biologist, but the reason they give me this, this class, astrobiology, because I'm a physicist, but I also know a little bit about biology, chemistry, and all these other things. And yeah, so I don't have any problem teaching it. I enjoy teaching it. I will teach it next semester, and probably other semesters that follows. But biology is, and technology associated with biology, it's the future, folks. It's the future. I think you should enjoy it.
So I know the conditions aren't optimal for a face-to-face class, and in the Snowmaster, we are going to reoffer all these taped talks again, and I would advise you to tell your friends that they can see these talks again. It will be in Snowmaster starting after Thanksgiving, and it might be useful. I know this class was capped out in February, and we really need to offer this material. I'm sorry it will all be just taped, but I think it'll be useful. And let's go to Turkey sometime. I can't imagine them understanding my English, but maybe we can have a good time. Now, thank you, Reza.
Oh, you're most welcome. So you folks have a healthy days to come. Thank you for your time.